what about loops? We are going to need some loops. So let's look at the following loop. And I'll start by looking at just E equals 0. Let's just take the nucleons and then scatter them again. So in terms of the momentum flow, I have some q, say, going this way, and then I have minus q going that way. That's my loop momenta. So I'd get two couplings C0. Let these be zeros. Integral d dq. And if I just kept the HQET type term in my kinetic term, then it would look like that. OK, so this is just, so for the moment, if we just keep partial dt in the kinetic term, which is what we were doing in HQET, then we would get that. And that's a bad integral. It's got a pinch singularity. It's an ill-defined integral. So just from that little algebra, we see that actually keeping just the partial d by dt in the kinetic term is not the right thing to do for this theory. And that's because the kinetic energy is a relevant operator in quantum mechanics. Whenever you wrote down the Schrodinger equation, you kept it. So the right power counting should have E, which is of order p squared over 2m. So the partial t term and the grad squared over m term should be the same size. So this is generically true of two heavy particles. They have a different power counting for the kinetic term. Than HQET. Any two heavy particles, whether it's two heavy quarks, two heavy nucleons, two heavy anything. All right, E should be of order p squared over 2m.
E being the kinetic energy?
E being the, so really what I mean here is just the partial t term in the action over there should be the same size as the grad squared over 2m term.
Have you pulled out the exponential?
Yeah, I have pulled out the mass, yeah. So just like in HQET, to get this partial t, we pulled out the mass. Then we have a kind of non-relativistic type expansion. And the difference here is that we need the partial t to be of order grad squared over 2m. And that leads to effectively counting velocities rather than, because you have to count energies different than p's. We won't spend too long talking about that because we have other things to discuss here. But this is a whole interesting subject in itself, the power counting and what it means. One thing that's kind of interesting here, which we won't cover, which I can't help but mention, is that say you did quarks, which was a gauge theory. This is not a gauge theory that we're talking about, but you could do a gauge theory that has this type of power counting, and it has exactly the same problem. Just replace these heavy nucleons by quarks, and replace this dot here by a Coulomb potential. Exactly the same problem if you try to use HQET. And in that theory, too, you need E to be of order p squared over 2m. That's called non-relativistic QCD. Or you could do heavy electrons, where you have QED as the gauge theory. Non-relativistic QED, same issue. E has to be of order p squared over 2m. And in gauge theory, there's even a further complication, which is basically that there's gauge particles that want to talk to E, and there's gauge particles that want to talk to P. And those are different sizes. So you have something called ultrasoft photons and soft photons that are the gauge particles for E and the gauge particles for P. Kind of an interesting theory. We won't have time to talk about it. If somebody wants to talk about it for their project, it's kind of fun. OK, so we have to keep p squared over 2m. Just knowing a little quantum mechanics, we know that that's true. Or running into this pinch singularity, we see that trying to do something different than that leads to problems. So let's redo our calculation here, but now keeping that term and see what we get. Same bubble diagram. Let me send in on each of these legs E over 2. So E is the total energy that I'm sending in. Convenient normalization. Let's see how having the kinetic energy fixes this pinch pull. Okay, so if you look at the poles in the complex plane here, what's happened is you've split them like this so that you've moved them along the real axis. And so now you can just think of a contour, for example, if you want to think in the complex Q0 plane, you can think of doing a contour integral like that. And everything is well defined, it converges at infinity. Everybody's happy. So we can close above, pick the pole where Q0 is E over 2 minus Q squared over 2m plus I0, plug it back into the other one. My notation is that n is going to be d minus 1. So when I do one of the integrals by contour, I go down a dimension. I'll call that n. So it's n here. This integral we can do. We have to be careful about the I epsilons. Because they tell us whether it's minus IP or plus IP. ME is is set up in my convention, ME is p squared. So this is giving a p, but it's giving either a minus IP or a plus IP, depending on the sign of the I0, but I know it's a minus IP. So I used dim reg here. Because if you look at this integral, there's 3 powers of q upstairs, 2 downstairs, so it's power law divergent. But we don't see power law divergences in dim reg, we just get this finite answer. And actually, that finite answer is exactly the imaginary part that you need if you want to cut this to graph and say that the cut of the forward scattering is the same as this amplitude squared. So it's exactly, in essence, this is the piece that you need to have to be there by unitarity. If you were to try to keep the E, you could think, well, maybe if I just kept the E in this calculation, it would solve this pinch problem. But it doesn't really do it, because if you really stick with the partial d by dt as your leading order action, then the equations of motion are E equals 0. So you have to take E equals 0 to go on shell. So you can't really avoid the pinch that way. You really have to take this kinetic term. You have to take the kinetic term to have both the partial dt and the grad squared over 2m. OK, any questions so far? All right. Well, there's something here that might bother you. We've got an m upstairs. M is big. M is the mass of the nucleon, and it's appearing upstairs. That's always a bad sign. Usually a bad sign. Well, at least it's something we should worry about. So let's figure out where all the m's are. Let's count all the m's in the theory, holding the momentum fixed. So if we hold the momentum fixed, then grad has no m's. But partial t scales like 1 over m. And correspondingly, t scales like m. Okay? X and grad don't scale, but partial t and t do. And that's exactly what makes these two terms the same size. So we can ask, what is the scaling of our nucleon field? And if we want to do that, we go back to our action. And we just say the action shouldn't have any scaling. T has a scaling, so there's an m in here. This guy here, the whole thing scales as 1 over m from what we just said over there. This m cancels that 1 over m, so this guy is therefore m to the 0. The nucleon field has no scaling with m. So then, once you've done the kinetic term to figure out the scaling of the nucleon field, you can do then any other interaction. So the power counting of the kinetic term is always what determines the power counting of the field. That's true in any theory, any effective theory, because that's basically the basis of the fluctuations you're describing by that field. And once you fix that counting, you've got all the counting you need, and now you can go count other operators, like the one with 2m derivatives. And this guy here just has, you can have just vector derivatives, no time derivatives, just vector derivatives, 2m of them, and nucleon fields. So there's no m's in there. That's m to the 0. And this guy here is an m. So this guy here, C2m, must be a 1 over m. So therefore, any C2m scales like 1 over m. And now you see it's not such a problem, because here I have two C0s. Each one of them scales like 1 over m. I pick up one more m in the numerator, and that just makes the whole thing scale like 1 over m, which is the same order that the tree level was scaling in m. The tree level was scaling like 1 over m. So the loop diagrams and the tree level both scale like 1 over m. And that's actually generically true, that because every time I add a loop, I add a coupling, and so those two m's can't compensate each other. So there's no issue with m's. So the one-bit graph is the same size as the tree level, and they both go like 1 over m. If you now do dimension counting, you can say, given that we've identified that the C has an m in it, if you ask about the dimensions of C, it's -2 minus 2m, because the dimensions of the nucleon field are 3/2. And we're doing some expansion in p much less than lambda, so just by dimensional power counting, we expect that the coefficients would be of the following size. We know that there's an m, and that it's the only m. And all the rest of the dimensions you should think of as being made up by the stuff you integrated out. So it could be the pion, for example, setting the scale lambda. So what you'd expect for the C2m's is that this is how big they are, and that the derivatives are then being suppressed because of these lambdas, and you're expanding for p much less than lambda. OK? Are we happy so far? All right. And we'll see that, when you do matching calculations, this m is always there, and this is just a nice, elegant way of figuring that out. Because this is a very simple argument. All right.
I don't know if I totally understand that argument. So how do you know that C2m
Goes like 1 over m?
Yeah, you know that.
So the kinetic term, so at first you know this, right? Yeah. Yeah, so I see. You're worried about whether there could be 1 over m squared corrections? Yeah. In principle, there could be 1 over m squared corrections from relativistic corrections, so that this would be the leading order term. Yeah, not worse than that. If we looked at the p cubed, p to the 4th over 8m cubed term, that term would have a higher power of m, and you could imagine that there's some relativistic corrections in the 4 nucleons as well. Yeah. So we'll work basically here at lowest order in the relativistic correction so that you could put in the relativistic corrections as well. All right. So we're basically stopping at that order, which is equivalent to quantum mechanics, but we could go further if we wanted to in this effective theory. So now let's think about other loop diagrams in the theory without relativistic corrections, just with these interactions. And let's insert the 2n and the 2m derivative operator on these vertices. You see all the loops look like this. They're all bubbles. And that's the same reason in HQET that you don't have any diagrams that you don't have diagrams that look like this, because these types of diagrams involve antiparticles, and we only have particles. So that's the beauty of a non-relativistic theory. You don't have any diagrams like that. You just have diagrams like this. And so basically, this whole theory is bubbles. It's the theory of bubbles. If you go through this loop diagram, you do the pole the same way. It's exactly the same two propagators. Then you get the same q squared minus me minus I0. And the only difference is you get powers of q in the numerator. And so this integral is one of the ones that shows up in here. And this integral, you can do the same kind of trick that you used when we were discussing field group definitions, where you basically take the top and organize it by adding and subtracting. So add and subtract me. Like that. And now you can think n and m are integers. Just expand this thing out. Some number of these factors, some number of these factors. But anytime you get one or more of these factors, it cancels the denominator, and then you end up with scaleless integrals. So basically, that means you can throw this piece away. So higher order derivatives actually just lead to MEs, whether they act inside or outside on the nucleon fields. They lead to a p squared.
You're using n to mean
Yeah, sorry. This m is a little m, and this is supposed to be a big m.
No.
Oh, n. Oh, yeah, I'm also using that, too. Sorry. Yes. This is an integer. Should call it j or something. And the other n is 3 minus 2 epsilon. Yeah, it's dangerous. All right. But this means that basically the graphs in this theory are very simple. So if we actually now consider the complete set of diagrams where we impose, we put the full amplitude in there, and we consider these bubbles, because of this fact that I just told you, which doesn't change when you insert more bubbles, the bubbles all decouple from each other. The contact interaction is decoupling them from each other. So here's a complete amplitude. With k insertions of the coupling and k minus 1 loops. Okay, so we just computed all the loop diagrams in the theory, and it's giving us something that we can sum. It's a geometric series. So this is for k minus 1 loops. We can sum them up. So if you like, I should have called this the kth term. And if I sum them up, cancel an I on each side, look at that. Let me write it again. Like this. So dividing out the numerator, rearranging the 4 pi over m's a little bit, I can write it like that. And then we can identify this thing here as p cotangent delta. Okay, so p cotangent delta from our effective theory, we've calculated it to be the sum over this, p2m, where now I've conveniently defined hatted coefficients, which are the following things. And that just cancels the m that's in the C2m's. So C2 hat scales like m to the 0. So that's just it's an obvious way of reorganizing things, given the factors of 4 pi over m that we knew had to sit out front of this S matrix calculation of the amplitude. So we can identify p cotangent delta as something that doesn't involve any m's, and that actually is also what we would expect for non-relativistic scattering. So then you can look at different waves, and you can look at this formula, and you can, doing 2 of them will show you how it works. So S wave is L equals 0. So that's something we can do a Taylor expansion in Pn. And this is what the Taylor series looks like. And this has exactly the form that we wanted. This is some constant 1 over a, which is the scattering length, some constant times p squared, which is called the effective range. And we see that expansion coming out. And we never had to specify what the potential was, because the effective theory was agnostic to what the potential was. That's the whole power of effective theory, that you don't need to know what the particles were that you were integrating out. They just give you some values for these coefficients. And those values exactly become the effective range and scattering length in this theory.
So they seem very dim ray dependent.
Yeah, we're going to talk about that. Yes. Yeah. That will encompass the second half of lecture. So we'll come to that momentarily. Let me just do one more wave just so you see L equals 1. In the L equals 1 case, there's no C0 hat. You need the derivatives to correspond to the wave. And so in this case, if you look at p cubed cotangent delta, the denominator starts at C2. And the reason why there was this p to the 2l plus 1 is just so that you get the extra p here, which compensates the p's downstairs. And again, this thing has a Taylor series. Same story as over there. We can identify the scattering length for the p wave as the 1 over C2 hat. Okay. So all the higher partial waves work the same way. And you just have to have p to the 2l plus 1 in front of your cotangent delta. Okay. So you can see how this generalizes to any L. So that proves this non-relativistic quantum mechanics theorem. And we did it without having to specify what the potential was, because the potential is encoded in these C's, and effectively that's like a basis expansion of the potential, but it's a fun one because it's in delta functions and derivatives of delta functions. So we're doing a local local effective field theory, which is not something you'd think of ever using for a basis. Well, maybe you would, but most people wouldn't think of using basis of derivatives of delta functions for quantum mechanics. Okay. Well, you'd hope we could do a little more than quantum mechanics, right?